Well, good morning, everybody. I hope you're doing well or afternoon, depending on where you're joining us from. Can everyone see my screen? I'm hoping yes. Yep, perfect. Thanks, Mark. We are just so excited to have you here today for our episode 9. Everything old is new again. So today's September 27th, and we have a great presentation in store for you. As always, we're always looking for good ideas for our upcoming webinars. This is the final one in 2023. So if you have an idea or something you'd love to see us talk about, reach out to myself, Mark, or anyone at Geoengineers, and we will see what we can do to make that happen. If you're not on our webinar list, let me know. Send me an email after this or put it in the chat and we'll get you added. And as always, we've been using Zoom for a while now. This seems to be the best platform for most of it. If your firm cannot access it and you're joining us from your Gmail, know that we're always willing to share the recording afterwards to be distributed to you and your staff. Similar to previous webinars, we have a completion certificate that we will distribute after today's webinar. You'll see it along with the recording. If you've attended previous webinars or you have gone onto our website to watch one that's been recorded, because we save all of them there, and you need something like this to self-report those PDHs, let us know. I can get that to you as well. And as a reminder, we'll be using the chat feature on Zoom for today's webinar. You can chat it directly to me, put it in the group. Our moderator will be asking questions towards the end of the presentation. I'm going to be putting these poll questions, you see them right here, out shortly. And so be ready to answer those. I'm trying to see if I can actually do the poll at the same time. How great is that? So as you can see on these questions, we are going to be asking how many of you perform hydraulic fracture calculations as part of your work, and do you understand the difference between drained and undrained soil strength parameters? It's just a good opportunity to kind of see who's in the audience today. Disclaimer, we do this, just the views and information and opinions expressed during today's webinar are solely of those of the individuals and do not necessarily represent those of their respective organizations. And now it's my pleasure to introduce our moderator, Mark Miller. He's done a few of these, so a familiar face. He's a principal engineer and national trenchless leader at Geoengineers. He's located in Springfield, Missouri. He brings over 18 years of trenchless experience as well as 25 years at Geo. He leads our national pipeline practice and has completed hundreds of HDD projects. Fun fact, and we've mentioned this before, but it's been a while, he loves to ride a motorcycle and is an amateur radio operator. So I feel like that's super unique, Mark. I love that. So I'm going to have Mark do a safety moment and I'm going to push out that poll. So Mark.
Yeah. Next slide, please. Hopefully you're using the version. Yeah, so this is a oldie but a goodie. It slips, trips, and falls. This is a picture of a horizontal directional drill site. And, this is a minefield. And, paying attention to where you're walking, is obviously it's, you need to be careful in situations like this. Don't be distracted by your phone. You have all sorts of things going on in this picture, all sorts of things. You could slip, trip, fall. There's moving equipment, there's rotating equipment, high pressure hoses. I guess, among basically it's situational awareness. Understand your surroundings, pay attention to your surroundings, and pay attention to where you're going, because a slip, trip, or a fall could easily be very detrimental to your health. My dad was actually paralyzed by tripping on a cord, so I know from firsthand experience that they can be very serious. So anyway, with that, let's get on to our introductions of our presenter, Trevor Hoyles. He's done one of these webinars before. He's been with Geo 25 years, like myself. And for the past 15 years, he's spent working almost exclusively on trenchless projects across the country for multiple different clients. And fun facts for him, he loves playing tennis, fixing watches, which I think is a very unique hobby as well. I had no idea, Trevor, and mountain biking. And also today I want to present our special guest, Dr. Ian Moore. He's a professor at Queen's University in Kingston, Canada. He's got 43 years studying buried pipelines and including construction Sorry, I got the poll thing pop up right in front of me. Thanks, April.
Sorry, that's just
Um,
what it does.
and so he explores buried pipeline mechanics using both analytical and physical testing methods. He's collaborated and researched with many projects with consultants, DOT, city engineers, that sort of thing. And probably the most musically talented of the bunch of us here. He's a cellist and plays professionally in a trio, basically jazz standards. So that was kind of one of the, I guess, impetus for the jazz music opening. So I guess with that, I guess I will ask, welcome everybody. Sorry, I didn't do that sooner, but welcome. Thanks for joining us. So today we're discussing advancements in hydraulic fracture analyses for HD applications, particularly for undrained conditions, because I think a lot of people that do this stuff don't know the difference and why that's significant. So Trevor's going to talk about that. And, one of the things with HDD projects is that there's become a lot more scrutiny with regards to frac outs, hydraulic fracture, frac outs. A lot of regulatory agencies are starting to become more savvy of the issue. While in many cases it's probably not a big problem, it's, optically it doesn't look good. It can give, a pipeline company or a utility company who's doing installations using HDDs can kind of give them a bad name or a bad reputation amongst the public. So, a lot of agencies have started to scrutinize it and actually required hydraulic fracture analyses to be completed for HDD projects. So, some of these agencies actually have requirements of the methodology that you're supposed to use. And some of them also have minimum factors of safety that you have to meet in order to get a permit. So we're just going to delve deeper into that. There's still a lot of unanswered questions with regard to hydraulic fracture and how to apply it, and maybe some edge cases that, nobody's really thought much about or experimented with yet. So anyway, Trevor, why don't you go ahead and march on?
Okay, am I unmuted now?
Yeah.
All right. Thank you, Mark. I appreciate that. So this topic of hydraulic fracture analysis, it's a big topic. There's a lot of facets to that. We're going to really focus in on really one specific aspect, and that's really the applicability of what's known as the Delft equation for fine-grained soils. The Delft equation is really the most widely known and widely used method for doing hydraulic fracture analysis. And a lot of times I think is a little bit misunderstood and potentially misapplied to fine-grained soils. A little bit of overview here. Just looking at the poll results. Looks like a mixed bag, as I would expect. I figured we were going to have a wide variety of knowledge base on this topic. So we're going to start off a little bit high level and kind of cover the history and fundamentals of what's called cavity expansion theory. And that's really the foundation of hydraulic fracture analysis and the Delft equation. And so then we're going to dive in a little bit into specifically the Delft equation, its application, and then present a few alternative methods for doing hydraulic fracture analysis for fine-grained or clayey soils. And then hopefully I'll wrap it up in time to give some opportunity for questions and discussion. So first thing I wanted to do was really provide a little bit of a better definition of what we're talking about when we refer to hydraulic fracture. Also, a common term or phrase you've maybe heard is inadvertent returns of drilling fluid. These two things or terms are sometimes used interchangeably, but I wanted to clarify there. Hydraulic fracture basically occurs when your annular drilling fluid pressure in a bored hole exceeds the capacity of the surrounding soil to contain that fluid and hold that pressure. Now, the difference between hydraulic fracture and inadvertent returns is that you can have hydraulic fracture occur, you can lose drilling fluid from around your borehole, but not have it make it all the way to the ground surface. Now, inadvertent returns are specifically referring to drilling fluid emerging at the ground surface or perhaps in a water body at the surface. So that's a distinction that I wanted to clarify. Also, hydraulic fracture, the word fracture is in that name, but that's really used generically to apply to loss of drilling fluid from the bored hole. But there's really all the science at this point suggests that there's two potential mechanisms of mud loss or failure when you have hydraulic fracture, and one of them fundamentally is really just shear failure, what we might call blowout, and the other is development of tensile fractures along the borehole wall that the drilling fluid then can be transmitted along and through and up to the ground surface. And it's important to understand these two different mechanisms of failure, because there are actually some different ways to analyze that and have to be aware of that. All right, so I just wanted to cover here the basics of what cavity expansion theory is. At the bottom line, cavity expansion theory is attempting to predict the stress and strain behavior of soil in response to a pressurized subsurface cavity. And what I'm showing here is a cross section of a bored hole or a cavity here. And the first bit of pressures here that I want to try and explain are the earth pressures. The soil does not feel stress until the internal pressure of your bored hole exceeds the earth pressures, which really it's just the weight of the soil and water in the vertical direction, and in the horizontal direction, that force may not be the same magnitude of pressure as in the vertical direction. For example, normally consolidated clay soils might have a horizontal stress of about 1/2 to 3/4 that of the magnitude in the vertical direction. Now, the relationship between the horizontal stress and the vertical stress from the earth pressures is defined by a value that we call K0, this coefficient K0. And so if we had a K0 of 0.5, that would mean our horizontal stresses are about 1/2 of the vertical stresses. And so that's important when we're doing hydraulic fracture calculations, to understand the stress state of the soil and what the minimum stress is. And that's oftentimes in the horizontal direction. Now, here on the right side of my screen, this is we'll call this an idealized stress strain curve for the soil surrounding a cavity. And in the x-axis, we have strain or cavity expansion increasing to the right, and then the annular pressure in the y-axis increasing upwards. So as the pressure in the bored hole increases, it first has to exceed those earth pressures, typically the horizontal pressure, before you even start to enter the elastic strain part of this curve, until we start to actually elastically strain that soil. And if we keep increasing that pressure, we move through this elastic zone of soil deformation, and then we hit we call the yield point, and we start to yield the soil. And at this point, a ring of plastically yielded soil begins to form around the cavity. And here we are at the stress strain curve right there. And then if we keep increasing that pressure, that plastic ring continues to grow and expand, and reaching further and further out into the soil mass. And as you can see here, our annular pressures are increasing, and eventually that plastic zone reaches a maximum limit where the formation can no longer resist those pressures, and we reach this, what we call a limit pressure or formation limit pressure. The radius of this plastic zone is an important factor that we'll discuss. It's an element in the analysis typically. And just for a general idea, the ratio of your cavity or your borehole radius to the maximum plastic radius, it ranges typically a maximum of 10 to 20. So for a 1 foot diameter pilot hole in an HDD with a 1/2 foot radius, you're going to range this maximum plastic zone is really going to be at about 10 feet. But you're really not getting much more out of that, the resistance of the soil surrounding your cavity there. So in terms of the analysis, there are a variety of input parameters when we're trying to calculate that limit pressure, that maximum limit pressure that I just went over. And first and foremost, and probably the most important, is the soil shear strength. And that strength can either be modeled as drained with a phi angle, or undrained and expressed as cohesion. And I'm going to go over that in a little more detail here on the next slide. One of the other really important factors that are considered is that K0 factor that I described earlier. And of course, the soil unit weight, the shear modulus, which is a function of Young's modulus of elasticity, and Poisson's ratio is important, as well as groundwater. Okay, so this concept of drained versus undrained shear strength is very important to understand. So when it comes to a drained shear strength, what happens is that as you have your normal force on your soil here on the x-axis, as this increases to our right, our shear strength here is increasing on the y-axis. And this line right here, that shows the relationship that as our normal force increases on our soil, so does our shear strength. And the amount in which your shear strength increases proportional to that normal stress is defined by this angle, which we call the phi angle. Now, I'd like to give you kind of a real world example of how this works. So, if you're walking on the beach, I'm sure many of you have walked on the beach where the sand is saturated, you're near the ocean water. And when you step on the sand, oftentimes you can see the water in that sand push out as you put your weight on the sand. And because the sand is relatively permeable, the water in the pore space of that sand can squeeze right out. The sand can kind of compress and the grains adjust, and it will get stronger as a result of your added weight on that sand. The thing is with clay, though, if you were to stand on saturated clay, you'd have to stand there probably for a week or more for the pore water pressure and that water to squeeze out of that clay and have any impact on the strength. And so if we have the same plot here with increasing normal stress, it doesn't matter. It does not affect our shear strength. Our shear strength stays the same. And so our shear strength is expressed only by cohesion here. And we have no phi angle. And really comes into play when we're doing our hydraulic fracture analysis. Before I really dive into the analysis, I want to summarize a bit of the history here. And this gets, back to the title of our webinar, Everything Old is New Again, because I think we're able to answer a lot of questions by going back into the documents in history, and really going back to the origins of the development of cavity expansion theory, which was really researched by a guy named Vesic and published in 1972. There was a lot of work on this that predated Vesic's paper in the 60s as it relates to pressure meter testing and even metals testing. But in 1988, a couple guys, Luger and Hargaden from Delft Geotechnics, took Vesic's cavity expansion work and applied it to HDD, specifically for use in hydraulic fracture analysis. And that became known as the Delft equation. In 1998, the Corps of Engineers worked with Delft and adopted the Delft equation with a little bit more clarity and detail, and adopted that equation and methodology to apply to core regulated projects. And then since that time, there's been a variety of different methods proposed and discussed. Just one of those, which I am going to bring up later, was developed by Kennedy. And his work was not really so much based on cavity expansion theory, but he really focused on that tensile failure mechanism, the development of tensile cracking and its involvement in inadvertent drilling fluid returns. And then in 2006 to 2009, our friend Ian here on our call, along with the doctorate student Hongwei Jia, worked on a new model for hydraulic fracture analysis in clay, and we refer to that as the Queen's equation for Queen's University. And then I felt like it is worth mentioning that the Corps of Engineers issued some new guidance in 2020 that clarified the use of the Delft equation and modified the approach a little bit. One of the main things they did was to clarify the use of K naught in calculating your formation limit pressures. As I mentioned, that is an important factor.
Hey, Trevor?
Yeah.
Yeah, I think that was one of the main things with the Delft equation from the beginning, is because it wasn't clear from the original paper that you should be applying a K naught to your vertical effective stress or vertical effective stress. So I think it was maybe better understood with the most recent core guidance.
Yeah, that's right. So I'm gonna do what I normally try to avoid and when I'm presenting. I try to avoid presenting equations, especially big gnarly equations. Those generally don't go over well. But this is unfortunately unavoidable for our topic today. I want to make a point with this equation. So this is the Delft equation. And there's a few things I want to point out. This symbol here is the symbol phi, and that is the phi angle for the drain strength that I was talking about before. As you can see, it occurs throughout the equation. Another thing I want to point out is this term right here, which is our R naught, which is the radius of our bored hole, our pilot hole, and RP max, which is our plastic radius. And basically what the Delft equation did, what Luger and Hargaden did, was take the Vesic cavity expansion equation and they modified it a bit to add the ability to allow the user to modify or limit that plastic radius to whatever the user wants. And so that's a certain level of conservatism you could build into the model by limiting that plastic radius. So, but what happens if you want to apply that Delft equation to fine-grained soils where we would expect undrained strength conditions would prevail? If you have a phi of 0, what happens is that all of these terms with phi in it, they all go to 0 or are undefined, and your equation becomes simply your confining stress plus cohesion, which is equal to basically the yield point of the soil. If you have the K naught value may technically affect your yield point, but this is essentially your yield point of your soil. And you would not be then allowing, this does not allow for any plastic deformation. So if you remember that stress strain plot that I provided earlier on, that yield point was right before we hit that plastic part of the curve. So that's what happens to the Delft equation. And this produces potentially a much lower limit pressure than actually the soil might be able to provide. And so I really wanted to look into, okay, what was the original intent of the Delft equation for fine-grained soils? Is it supposed to be applied this way? And so I looked back in history to try to look for a little bit more clarity on this, because the values we get from this equation appear to be relatively conservative based on what we know and based on our actual experience on projects. One thing of note that I find interesting, if you go back to the original Luger and Hargadon paper where they proposed this method in 1988, they had a case or an example in clay soils. And here they say, well, the internal friction angle phi was negligible, and then in parentheses, they didn't really point this out overtly, that whether to use drained or undrained strength parameters. I thought it was an interesting hint that they said, say 0.1 degrees. So from a soil mechanics standpoint, that is absolutely negligible, really should not make any kind of difference in the overall strength of your material. But I think by saying this, what they meant to suggest is that you really would need to have at least a 0.1 degree phi in that equation for all those terms not to cancel out.
Yeah, Trevor, I would add that, if you try to put the Delft equation into a spreadsheet and then you plug in a 0 phi value for phi, it just doesn't work, right? And so you actually have to do the reduction of the equation to reduce it like you did, but it doesn't work in a spreadsheet. So maybe that's why they used very minimal friction angle.
Yeah. And a lot of people have been doing that. And one of the reasons we're doing this webinar today is because there has been historically a lot of confusion. Should we kind of be faking it and putting in a small phi into the equation? Should we be using 0? Perhaps using a different equation altogether? I thought it was interesting going back to Vesik's original paper on which Delft developed their equation. What we found is that the Vesik paper for cavity expansion theory actually provided 2 different equations. One for drain conditions in sand, where phi is greater than 0, and then a different one in clay soils where phi equals 0. And as it turned out, one of my very smart colleagues was able to do some solid math and basically be able to see that the Delft equation more or less matches the Vesik equation, with the fundamental addition that Delft added to this equation was to provide that extra term that allows the user to input the maximum plastic radius. That was really the fundamental distinction between Delft and just the basic cavity expansion equation for drain conditions. So what we've been able to show is that the Delft equation really is founded on the drained only equation for cavity expansion theory. And there is a different equation that exists for clay soils, as you can see, does not have phi in it. And so we wouldn't have to worry about any terms being canceled out. Now, take a step forward back, to 20 years plus later. Ian and Hongwei Jia worked on a new method to predict the formation limit pressure in clays. And that's what we refer to as the Queen's equation. This Queen's equation is fundamentally premised on cavity expansion theory. And just like Delft did with Vesik's equation for drain conditions, the Queen's equation does a similar thing for the undrained equation in Vesik, in that it adds a term for R naught over RP so that the user can limit the plastic radius if they like. And the other thing it does is it accounts for the stress state of the soil, and it accounts for this K naught factor, which ends up being fairly important. And as you'll note, there's one version of the equation for K naughts less than 1 and one version for K naughts greater than 1. Now, I want to give everybody an idea of how big of a difference it makes in what equation you use and what method you use in terms of what calculated limit pressure you come up with. So this line that I'm showing right here in the x-axis is showing varying undrained shear strength of a theoretical soil. And then the y-axis are calculated formation limit pressures. So this line right here is showing Delft with a phi of 0. And this is for an example at a depth of 35 feet with a typical soil of unit weight, 120 pounds per cubic foot, and a K naught of 0.5. And so our R naught over RP is 1, meaning the radius of our hole is equal to our plastic radius, such that there is no plastic radius. So we're not allowing any plastic deformation here. Now, if we plot the Vesik and the Queen's equation, so Vesik is up here and would, in my opinion, represent sort of the upper bound for the limit pressures. And Queen's is very similar to Vesik. And one thing I'll mention of note, when K naught is 1, Queen's and Vesik are the same. And depending on your K naught value, your Queen's equation will change and be less than this theoretical maximum, because it does account for that K naught. And so the other thing about these two lines I've plotted, I've set the plastic radius to be 20 times the borehole radius. So this is basically for a 6-inch radius hole, 10-foot diameter plastic radius, which is really the maximum plastic radius. So if we were to make it 100 feet, it really would not change this value. This represents sort of the theoretical maximum. So the question becomes, okay, this is sort of an upper bound for maximum plastic radius, and del phi of 0 is really a low bound with no allowable plastic radius. And I think I should point out that bear in mind that if a user were to apply a drain strength to a fine-grained material and improperly use a drain strength with a phi angle and use the Delft equation with a phi angle, your calculated formation limit pressures would be on the scale of 1.5 to 2 times even the upper bound for Vesic and Queen's for undrained equations. So if you improperly use drained conditions, you could be over predicting your limit pressures by a magnitude of 2 to 3. Whereas if you apply a phi of 0 and use the Delft equation, you could be potentially under predicting by a factor of 1.5 to 2 times or more. So I think that's important to point out. And the other thing I wanted to mention is that a lot of practitioners do like to limit that plastic radius, say to 2 or 3 feet, and then also apply a safety factor on top of that. And what can happen is, if you're not careful, depending on how much you limit that plastic radius and how much of a safety factor you apply, you could end up with a formation limit pressure well below even the yield pressure and be exceedingly conservative. So that concludes my technical presentation today, and now I just kind of wanted to open it up for questions and discussion.
Hey, or Ian, I had a question for you. I mean, we need to get you kind of involved here. So, we have some people that, it's kind of segues what Trevor was just saying, but we have some people that think that, basically we shouldn't allow plastic deformation. Do you think that's, to prevent plastic deformation around the hole? Do you think that's a reasonable limit, or do you think that's too conservative? And also, just answer that. I guess a good place to start.
Yeah. Well, first, before I do that, I great job, Trevor. I thought you explained the history very well, and just the introductory soil mechanics on shear strength and so on. Great job. I think that using a pressure that relates to initial yield at the borehole, in other words, that RP over R0 equals 1, is definitely too conservative. Basically, what you're doing, if you use that approach, you're ignoring the shear strength of all of that overlying material. All you're doing is just saying, okay, I'm concerned about the shear strength of that little strip that's around my borehole, but I'm going to ignore all that reserve strength that I've got going. Sort of looking for an analogy, it would be like designing a reinforced concrete beam where you design for first cracking of the concrete and you ignore the steel, which, reinforced concrete, of course, you rely on the steel to provide that tensile strength in that tensile zone. I just don't see why you'd think it would be reasonable to ignore that. That soil has strength. There's no question about it. We've actually been studying stratified materials with some experiments in sand. It's difficult to do experiments in the lab in clay. And we're sort of getting confirmation of the role of those overlying materials controlling strength. They're definitely present. Why not use them? I just don't think we could. I would suggest that it would mean that you couldn't do directional drilling in a lot of reasonable sites, and you'd have to do something like cut and cover, or I don't know. There's river crossings and that, which would be very challenging. Unnecessarily, just for the sake of, we need to be conservative, yes, but we need to be reasonable when we're conservative. So I think that's too conservative. So I don't know if I'm overstating my objection, but I just don't think it's a reasonable thing to ignore that shear strength. Another thing would be designing a footing and just using a little bit of shear strength near the footing and forgetting it and not considering the underlying strength of the material. It just doesn't make sense to me. So a long answer to a short question. A long and somewhat passionate answer to a short question. Thanks, Mark.
Thanks, Ian. One follow-up to that, there's a lot of folks that think that those pressures do need to be limited to something less than that ultimate limit pressure defined by cavity expansion because of the fear of the development of those tensile cracks that can occur before that full plastic radius can be in effect. And I get that, and I know some of your studies show the development of tensile cracks. And one thing I meant to point out a little more clearly, in that Queen's equation and Queen's methodology that I've described, there is a component that I didn't have time to really go over. There is a component to the method that attempts to predict if tensile cracking or failure will occur prior to that full limit pressure. And, a lot of that was based on that work of Kennedy that I described earlier. And I would encourage, we don't have time to really get into that here, but I would encourage everybody to look at the original paper from 2006 if you're interested in that and understanding when perhaps tensile fracture could be the controlling or limiting factor. But what I will say in general at a very high level is that it appears that you're most at risk of having tensile fracture control or limit your pressures when you've got really high K0 values and particularly high strength combined.
Consolidated clays. Yeah. So you're absolutely right. So that work with Matt Kennedy, we defined, it's actually the equations are a lot simpler if you have tensile fracture. So the equations can be put into your spreadsheet, but also we developed a solution. And again, it's pretty straightforward, simpler than the equations for maximum pressure for the plastic cavity expansion. But an expression that allows you to decide, is it going to fail in cracking or is it going to fail with shear strength or blowout? And so you don't have to sort of apply a factor of safety because, well, maybe it'll crack. Well, you can just calculate whether it's going to crack or not and explicitly account for it. One of the companies that's using my work just applies the tensile fracture criterion because typically it's lower than the plastic cavity expansion solution. But it's not hard to program these things into a spreadsheet, even though as somebody very cleverly commented in the things, there weren't spreadsheets in 1972. And the early spreadsheets, those of us who were using them when they first came out were pretty clunky. But it's so easy now, although very easy to make a mistake, of course, in the equations as well. But yeah, just program it in and account for it explicitly, so you don't have to apply some sort of factor of safety to out of concern that there might be a mechanism that develops it that you haven't considered. There was something rather else I was thinking of mentioning, but I can't think of it now. So I'll be quiet and wait for the next question.
Yes, I would, we talked about, sandy granular soils behaving in undrained conditions and clay soils, undrained conditions. And, I guess one of the things to point out is just, you have to consider the speed at which the drilling takes place, right? So that's kind of the big differentiator, but there's other factors there too with, there's mixtures of soils, not everything is a sand or a clay, you have these mixtures. And how do Ian, if anybody's really done any work on, say pore pressure dissipation with different gradations of soils, maybe a sand with silt, a silty sand, a sandy silt, and to, maybe, because going one direction, either fully drained or fully undrained is, maybe there's some good nuance that could be looked into in the future to give us even better predictions.
What a great comment. So when it comes to hydraulic conductivity, which is what controls consolidation or drainage under, dissipation of excess pore pressure, the release of that increased stress from the water where it initially is applied, or a lot of it's carried by the water, into the soil particles. And it requires that release into the soil particles for friction between those particles to develop or be affected and the frictional strength to be increased. but that hydraulic conductivity is very much controlled by the fine particles in the soil mix. So you could put 10% clay into sand, and the hydraulic conductivity is going to be much closer to clay than it is to sand, right? I mean, and I don't think that really needs to be explained. It's sort of fairly obvious. And so there is research and there are results for these mixed materials, not explicitly for that I'm aware of for cavity expansion solutions, but for hydraulic conductivity. And then just looking at hydraulic conductivity as a sort of, I'm going to call it an index. It's a parameter that controls consolidation or dissipation of or drainage. But whether it's 10 to the minus 6 or 10 to the minus 12 or 10 to the minus 11, it'll give you a ballpark idea of where it is relative to a clay and a sand. And I think there's lots of materials with fines, like fine silts, that are going to be much closer to undrained behavior than they are to drained behavior. And as soon as there's a reasonable amount of clay in there, it's going to be very much, I think, an undrained response.
Yeah, I totally agree. And that's such a tough question to answer confidently. That generally we treat silts as undrained, and that's, I think, the safe way to look at that. And even sands with high silt content, silty sands with 30-40% fines, we would potentially look at as undrained. I'm noticing some questions come in here. There was one about how would we determine K0 for over-consolidated soils without lab testing. Good question, and I can tell you K0 is a very difficult parameter to estimate in general, whether it's normally consolidated or over-consolidated. Some of the in-situ testing, like CPTs, it can help with that, pressure meter testing. But short of bringing out a specialized CPT or pressure meter rig, like the question asked about, without lab testing. Well, you got to do the lab testing, and we'll, potentially do a consolidation test to estimate the K0. Of course, you have to accept that there's going to be some sample disturbance there. But really heavily over-consolidated soils, sometimes you might not even be able to get an underserved sample, a Shelby tube in that material. And perhaps maybe that was what Andrew was getting at.
Can I jump in there, Trevor?
Yeah.
There are some pretty good empirical correlations. If you had a major project where you're installing a 36-inch pipe using drilling, like something that's going to be expensive if it goes wrong, maybe it is justified to bring out a pressure meter. There are companies that just offer that service. I don't know how much it costs, but it's probably a lot less than the cost of a big project going wrong. Okay. But for your regular small diameter installs, there are these correlations where K0 and is related to over-consolidation ratio. We're pretty good at doing consolidation tests or odometer tests. And with an odometer test, you can determine the pre-consolidation pressure, and you can calculate the current overburden pressure and get the over-consolidation ratio. And there are correlations between over-consolidation ratio, which is the maximum pressure it's ever experienced in its history, due to glaciation or erosion or some other process, divided by the current pressure. And those correlations, actually a lot of them were initiated at MIT back in the 60s and 70s. But they're pretty good, and you can get a decent answer. Those correlations can be related to various parameters that are easily, like simple Atterberg limits. And it's a starting point. I'm not saying it's going to give you an accurate answer. I don't know if you guys use those sorts of correlations in your practice, but it's a great place to start if you're saying, well, what might the pre-consolidation pressure, what might the K0, be?
Yes, to answer your question, we do use those correlations.
We had another question here. How about alluvial areas where there are multiple small strata or lenses of sands and silts? And I can kind of take part of that, and somebody else can chime in. But what we do is when we look at a site, an HDD site, we take the site, and usually we've got more than one boring. So we've got a series of borings, and we divide that distance into zones. So vertical zones that are similar based on the borings. And then we take within that boring, we try to define the soil layers with depth, and we can have as many soil layers as we like. But we do try to generalize a little bit. If we have let's say one sample of a sand, that's surrounded by silt or clay, oftentimes we won't even model it, because we have no idea how the lateral extent of that unit might be. If it's that thin, it could just be a lens that, the drill profile may not even encounter. So we try to simplify and group things into more, we kind of turn the resolution down, I guess, for lack of a better term. I know, Trevor, if you have any additional thoughts on that.
Yeah, I mean, and what you would do is you would model it based on, if you have interbedded layers of differing material, you would model it with the weaker material to be conservative, and discount thin layers of stronger material if you don't think it's thick enough to affect it. And that kind of also gets back to the discussion about the plastic radius. If you happen to be, for whatever reason, forced to be at a certain elevation in your HDD design, and you're only maybe potentially 2 or 3 feet below perhaps a weaker layer, you could potentially constrain that plastic radius to just the layer you're analyzing, so that you're not trying to account for that overlying stronger layer.
Yeah, that's a good point, because, a lot of the original hydraulic fracture calculations, well, Delft, for instance, said, well, in sands, you would use an RP max value of 2/3 the depth of the profile, right? And then in clays, you would use 50% of the depth. But really what you need to consider is the depth of the drill profile within that certain unit, not from the ground surface. So something to consider when you're doing these calculations.
I would agree. But with the proviso, as per the previous comments, that if those overlying materials are stronger,
right,
you can just assume that it's that weaker layer all the way to the surface.
Yeah.
Of course, it's not that common. I mean, geologically, it's sort of tricky to get a material that's weaker below a stronger layer. But I mean, of course, if it's sand versus clay, that happens. But it's not that common to have a lower density, lower 5 layer under a higher one.
Yeah, it's not uncommon where we'll run an analysis on a design that we've performed, and if for whatever reason the bottom of the drill is in a clay soil, the risk of hydraulic fracture can look pretty bad. But if we evaluate the risk of hydraulic fracture in the sand, the risk is so much lower, and so it's something to be considered. And sometimes, you might have to design your HDD profile in a deeper clay layer with a higher risk of hydraulic fracture, but knowing that you have this sand layer above you that can prevent that from propagating to the surface. Now,
it's a reserve capacity for you.
Yeah, although you do have to make some assumptions of the lateral extent and uniformity of that overlying layer, right? So you do have to be careful when making some of those assumptions.
I'm seeing a few other questions here. What about areas where gravel is encountered? So generally, your bigger risk associated with gravel is what we call formational fluid loss. So you're going to potentially have a risk of drilling fluid entering the gravel formation, not through deformation of the gravel. It's generally pretty strong material, but because of all that open pore space, you can just lose drilling fluid into that formation and potentially have inadvertent returns with that, although it's pretty uncommon because generally gravel is so problematic for HDDs from a variety of standpoints. Where we have significant gravel, we just don't HDD for a variety of reasons, including hole stability and cuttings removal.
Yeah, if you have a lot of formational fluid loss in an open gravel, you've probably got other problems.
You got other problems for sure. The bentonite wall cake, does that change things? You know, the wall cake really helps with regard to hole stability. That's the big function of the wall cake. You know, I don't think it's really taken into account for cavity expansion theory or the behavior of the soils. Although I wouldn't be totally shocked if some folks have possibly looked at the role of that. And I don't know, Ian, if
okay. So that's something I have studied.
Okay.
Not with respect to, of course, drilling in clay, which is today's sort of main focus, because you just don't get filter cake because you don't get that flow of material of moisture into the clay. But we've certainly done experiments with sand, and we've done both sort of one-dimensional experiments where you get some sand and you get a typical drilling mud with the typical HDD additives and so on, and look at, well, how much filter cake do you get? What sort of strength do you get? Turns out it adds almost no, based on our experiments, it adds almost no additional capacity, because that filter cake is basically a little layer of clay, which is not very strong. And the sand and the shear strength of the sand, as Trevor was pointing out earlier in his presentation, is dominant. And you get much higher capacity from that frictional strength of the sand. So everything that I've done looking at filter cake, so initially I focused a lot of attention on it because I believed that it would likely control the phenomenon. Turns out I've seen no evidence that it, even if you get a good filter cake forming, that it does anything for you. So you just, my current thinking is you just neglect it.
That makes sense.
Thanks, Ian. You know, we probably ought to be wrapping up here shortly. I was going to give you, I was kind of curious because you are working on some current research for hydraulic fracture in sand. Is that correct?
Thanks, Mark. I really appreciate that, mate. It's nice to have an opportunity to talk about some of the other work that I've been doing specifically in coarse-grained materials. And so one of the big challenges we have with this body of work is the paucity of experiments. There's essentially been no prototype scale experiments under control conditions. Of course, lots of activity in the field where you don't really know what soil materials you've got, what the densities are, and so on, and what the applied mud pressures necessarily are. But in the lab, very little. However, I had another student, Hoyles Lan, who finished his PhD a couple of years ago now, and we've been publishing. And he conducted a series of experiments in sand, initially just in uniform sand, at a whole range of burial depths, or I should say depth to diameter ratios for his experiments, and also stratified coarse-grained materials where you've got a lower density, weaker material over a stronger material, and where you have a stronger material over a weaker material. And that's all been pretty much published now. And we've also shown how to do two-dimensional analysis, finite element analysis, the sort of stuff that would be pretty straightforward with a program like FLAC, if you have access to FLAC, and there's lots of other programs. It's just that's a particularly easy program to use, much easier than a beast like Abacus or something. And so if you've got a specific stratigraphy that you're concerned about, we've got evidence that the analysis works, and that evidence is, of course, is experiments. So that's where a lot of the current focus has been. I'd love to do some experiments in clay, but it's devilishly hard to produce large, good quality blocks of clay to do prototype scale experiments in the laboratory. Thanks, Mark.
Well,
Yeah,
it
sure.
sounds like we've got a future topic for the next for a webinar next year, perhaps.
I love it. Well, Dr. Ian Moore, thank you for being our special guest today. Trevor, as always, great job presenting and taking the time to share this information. And Mark, thanks for moderating this great discussion in the chat and messages that I'm seeing. Everyone's really appreciative for this discussion. They really enjoyed it. So thank you. I will be sending out an email here in the next day or so with the recording of this webinar, as well as the certificate of completion. So watch your email for that. And as I mentioned, this is the last one of our webinars for 2023. So stay tuned for our 2024 agenda. And we're excited to continue this moving forward, and let us know if you have topics. We love it. Anything that comes to mind, toss our way. We particularly like the discussion format. So thanks so much. Have a great rest of your week, and reach out if you need anything.
Thanks, everybody.
Thanks, everybody. See you later.
Cheers.